Dear student, just learn something from this small video. Today, topics is Orgel diagram for spectroscopic term. Term means level, means it reflect the idea of orbital. As you know, from spin orbit coupling or LS coupling or RS coupling, as you have learned in the previous semester. Now, just remember all these things. Here, Orgel diagram, the diagram will show the relative energies of electronic terms in transition metal complex and other similar, was similar to Tenebo-Sugano diagram, which will be learned. I will dot teach you later. Now, this diagram get named after the creator Leslie Orgel. Its Orgel diagram mainly restricted to only weak field, that is to high field. For the weak field ligand, we will get high spin, and for the strong field ligand, we will get low spin. What is the meaning of low spin and high spin? Just remember, maximum number of unpaired or electron in the species give maximum or large magnetic moment due to the maximum number of unpaired electron. That means higher the number of unpaired electron, higher is spin. As you know, from the magnetic moment root over n plus 2, where n is the number of unpaired electron. There is no information about the strong field reflecting low field because is qualitative. No energy calculation can be performed. The symmetry only show symmetry state of the highest spin multiplicity. That means maximum pairing, maximum number on pair electron parallel spin. We can say another term. This is number of spin allowed transition. As we know, allowed transition for forbidden transition. In Orgel diagram, the parent term PDF, that is, as we know, S orbital, P orbital, D orbital, F orbital, G orbital, etc., etc. That is. So there are two types of Orgel diagram. One showing D1, D4, D6, and D9 configuration. Other one showing D2, D3, D7, and D8 configuration. All these two set 1, 3, 4, 6, 9 give another term, and the 2, 3, 7, 8 give another term. Now, to understand the Orgel diagram, we have to remember the molecular symbol. Means is a characteristic table containing information, and this is the very important historical point. Nobel Prize awarded this scientist. Now come to the point. Molecular symbol, we can mention here A or B. Generally, A means one dimension, that is singly degenerate orbital, and for example, S orbital or S too similar to S, having only one degenerate state, only one degenerate level. A means generally reflect on the positive side, B on the negative side. E means two-dimensional, means double degenerate. T means triply degenerate, and G means 4 degenerate. Ice means 5 degenerate. It is like this. For the understanding, come to this term symbol, molecular symbol, and the splitting. As we know, the term symbol. It is a very important part. As we know, spectroscopic term or level, that is S, P, D, F, G. These are the very important for this. In the case three-dimensional view octahedral and three-dimensional view tetrahedral, um, S represent A because here single S. G means Garrett, reflecting the symmetry. Here G is absent because in tetrahedral, as we know, there is no symmetry, meaning no center of symmetry. That is why P means triple E. In P we have three double E degenerate X, Y, Z, and D we have five. Five means two set double E degenerate, triple E degenerate, and here also D also removal of G only, and F this thing A 2G and the T1G, T2G, and like that. Here T2G is random use, rarely used, sometimes not used. But see here we have four set A1G, EG, T1G, T2G. Then in the tetrahedral we have the removal of this. And some important point from the group theory we have to know. Symbol used to identify irreducible representation of group. Here A singly in the first part of the slide I mentioned here. This is the A, B, E. This one X means any just A or T, E or Z, as we name E, Z, T1, G like that. And one means when A or B, the sign of wave function does not change, and here 2 means the sign of wave function changes. Only this upon the rotation about the center of atom, and sometimes this symbol symmetric in the case of double mark means asymmetric with respect to horizontal symmetry plane. Just remember to the group theory symmetry operation. From that point also you can learn G Garrett symmetry, U ungarrett, and any antisymmetry, that is unsymmetry to the center of atom like that. Just remember this is principal axis having the maximum number of electron atom reflecting. Then presentation of Orgel diagram. For the to reflect the Orgel diagram, we have to remember some important points. Number one, reflect or write down the spin multiplicity of ground and the excited free atom, free ion term in this diagram. And number two, write down the same multiplicity for the term S. For the terms, this should be terms here. Some gap is due to some typing mistake obtained by splitting of terms on the right subscript G case of for the because in octahedral there are central symmetry. Weak field, as we know, weak field reflect I spin. So then show all the possible transition from ground to different excited state. Means transition should take from ground state to excited. That is from one level to second level to third, like that, as we learn in the electronic transition. Here some energy electronic configuration. That is for the D means this chapter will generally reflect the transition. All the transition take place in D or vital in different energy level. D1, D9, D2, D8, D7, D10, D4, D6. For example, I have given like this. Here in the D, it gives D term means 2D. For D1 and the D9, we will get D term. D term we have the transition. This is the ground state, and this is the excited state. And for D2 and DT, we have 3F for F term, D term, F term. Here in the F, from the whole sequence of electronic configuration, D means from starting from energy level 3, F means starting from energy level 4. That means n minus 1 in case of D and n plus n minus 2 in case of F. the D and the F, we have to pass S and P. Minerally, P is very near to the S. This is why P, the first P excited. In the case of the term, we will get P orbital. This is 3. We have to put this three like that. P excited. In the P, we have get triply. This one, one T1G, and in another, this one. These are the F, 3 T1G. I mentioned the F because for this is F, and this is also T1G. This is also T1G. This is why to identify. This is for F. This is from F. This is from P. This is why P orbital, F orbital. 3 G and the 3A2G. These are the F form. With addition to this, and come to the 3D and 37. These are the 4F term. We have there also 4P like that in case of 3P, because this is also F and F same category. Only thing the multiplicity is different. That is why multiplicity is given by 2s plus 1 or n minus n plus 1, where s means spin value. If it is 1, half, and it is 2, that is half plus half to 1, or it depends on the orientation of the spin. If it is opposite direction, it will get cancelled. That is why half minus half, we will get 0. So you can, I will show in the next slide. So this is, and the D4 and D6 also, D term, this only spin multiplicity is 5. That is why 5D. It reflect 5 because this is why only 2, 5D, 2D, and 5EG. C, term of D1 to D10 configuration. Let us learn. This is for D1, just reflecting the orbital electronic configuration. This one, 1 electron in this particular R5 orbital. So the summation of L, this is the summation of L, will give the L, that is L value. That means no need to see this blank orbital, only see it reflect plus 2, that is 2. 2 means D spectroscopy. Like this, you can calculate all this D1 to D10. In D5 and D7 and D10, we have half fill stable and full fill stable. It reflect S term, because plus 1, plus 2, plus 2, plus 1, 0, minus 1, minus 2, all together. When we sum up, we will get 0. That is why 0 means S level, S term. Now, then number on pair electron is 5. It is 5 plus 1, 6. It gives the multiplicity. When putting the value of J, we will get the term symbol. Just remember all that also. In the same D10 also, all this get cancellation. That is why it reflects as L value 0 means S. There is no unpaired electron. It is 2s plus 1, 2s plus 1, or n plus 1. From that value, only the 1. That is 1 multiplicity singlet. That is, it reflects this one. This is why singlet A1G, singlet A1G, multiplicity 6. We put the 6, multiplicity 1. We put the 1. So remember this thing. And the term symbol and molecule symbol. Yeah, just I remember, just I focus on the previous slide also. I don't need to repeat. Just remember this 1 dimension, 2 dimension, 3 dimension. To remember this. Then Orgel diagram for D1 and D10. Why I am selecting D1 and D, give the D term. Give the just see D1 and the D10. This is also 2D. This is also 2D. This is why the same case. So just this is one. For example, we have taken one example, hexa echo titanium 2 D1 configuration related to T2 term. So this electron yeah, in the ground level 2T, and this one means here 1 electron present, then 0 means no electron present. After absorbing the UV radiation, the electron get excited, then there is no electron and 1 electron here in the EG. This is called electronic transition. For this transition, we have, this is the term Orgel diagram. So the transition takes place to 2T2G to 2EG. This is the energy gap. It is related to this H nu, meaning delta H or delta O or delta naught. We can say related to, means according to Einstein Planck's energy equal to H nu. Remember that thing. Just energy absorption when here frequency. This is some related graph. Now here the magnitude of splitting depend on the nature of ligand. It should be ligand. And also affect the frequency of absorption. Weak field correspond laser value. When it is weak, its gap is shorter. If it is stronger, its gap is larger. But generally, this Orgel diagram reflect strong field, weak field, and a high spin ligand. Generally, to remember this thing, higher the value of stronger the value of ligand, and weaker the value of ligand. That is the related, mean weaker field correspond strong lesser value of energy, and the strong related to larger value, like this. Two type of Orgel diagram, as I mentioned, that is D Orgel diagram and F Orgel. In the D Orgel diagram, we have these 4 type of configuration: D1, D4, D6, D9. And in the F Orgel diagram, we have D2, D3, D7, D8 configuration. That is, Orgel diagram will, however, show the number of spin allowed transition along with their respective symmetry designation. Thus, we have the symbol designation for the S1, for the S orbital A1G, like that. In the Orgel diagram, the parent terms P, D, or F in the presence of no ligand field is located in center of the diagram. Just without a ligand, the center I will show in the next slide. With term due to that electronic configuration in the ligand field. So let's see now. This is the D term. This is the in this center, no ligand field. And after getting the field influence, we have this from starting from this, you can go from this left side and the right side. Here two type of way, left and the right. This part left and this part right. And the left wing, in the left wing, the one electronic transition is expected. Means in this case, only one electronic transition will happen from, suppose, E to T or T to E. You put, this is removal of G or adding of G. We can get octahedral. In case of after adding the G, after removing the G, you'll get tetrahedral. Just remember, or that thing, no problem. Here, left side and right side. In the left side contain D1, D6. It reflect tetrahedral. D4, D9, it reflect octahedral. Just remember, D1, D6, D4, D9, octahedral. In the right side, D4 and the D9, tetrahedral, and D1 and the D6 octahedral, just opposite to this. So this is why, as we know in the orbital orientation from the splitting, dihedral and tetrahedral is just opposite to the splitting. In case of dihedral, triple D goes up. In the case of tetrahedral, triple D goes up. In case of dihedral, double D goes up from the energy barrier, from the center point. For the symmetry, we put the subscript G, as I mentioned. So this is for the F Orgel diagram. In the F, another P we will include. This is the left side and the right side. The left side, just D1, D7 tetrahedral, D3, D8 octahedral, and the right side D7, D8, D3 and D8 tetrahedral, D2, and high spin D7. This is high spin. Just remember this thing. High spin D7 octahedral, not low spin. Just remember how to electron get distributed to get high spin. Just remember from the splitting point. Then let's see some sum up in the for the D Orgel diagram, only one transition. That is why no problem. But in this case, three transition. Three transition. Let's see. In Orgel, three electronic transition is expected in this. One to this, one to this, one to this, like this. Next, come to this here. In the left wing, we will get this one. This is the ground state. A to G. From A to G to A2 to T2, T1, T1P, like this. This is the it absorb less energy, more energy, and highest energy. This is why. In this case, on the right wing, the ground state is what? T1G. Just opposite to this. T1G to the ground state. From T1G to T2G, A2G, and 1 T1GP. This is for the right, not confused. On the right, D3, D8 tetrahedral, and the D2, D7 octahedral. If the given part is tetrahedral or octahedral, for that information, just this part very important. Don't confuse. For D3 and the D8 configuration, in case of tetrahedral, it should be on the right, and D2, D7 octahedral, it should be on the right. So the energy transition is reversed to the left. That is why sometimes you get confused. So to protect or to get neutralized from that confusion, just remember this thing, either left or right. Or this thing very important. All the D1, D2, any configuration between the 5 is different. -5 +5, because 5 is very important center point. And on this left side, this is the possible transition having this one highest energy, middle, and lowest in the case of just the opposite to this. So this is the some question already frequently asked. So I hope you can learn something through this video. If you have any confusion, you can ask. Thank you.